Hello everyone. Here's a review for unit test number 4. This is basically an example of the problem set number 4. And recall that you must take problem set number 4 before taking unit test number 4, and we have a restriction here that you score at least 50% on problem set number 4 to be eligible to take unit test number 4. So the first page is basically many questions involving laws of exponents, and recall the rules. And what you could do, if you like, in this situation is regroup the coefficients, -4 and 3 together, and they're being multiplied, of course, and regroup the common bases of x squared and x to the 5th together. That step's entirely optional. You could just simply look at it and know to multiply -4 times 3 to get -12. And when multiplying common bases, x squared times x to the 5th, recall that we add the exponents. So x to the 7th. Similarly here, just an extension of the concept. And again, if you like, you could group the coefficients together, group the common factors, p to the 4th and p in this case, q and q to the 6th. So you can group those together as well, and then perform the multiplication separately and keep it as a product, of course. But it's not necessary, once again, to write this middle step. You can slide some 1s in here, if you like, at either point, as the exponents on the q and the p, respectively. And multiplying -3 times 9, we get -27. P to the 4th times p, we add the exponents, keep the base of p, 4 plus 1 is 5. And multiplying the q's as a common base, you keep the base q, adding the exponents, 1 plus 6 is 7. Okay, so that basically exercises the product rule for exponents. Next pair of examples, C and D, show the power rule. And these intermediate steps you could skip. But if you like, you can show the intermediate steps where you're taking each factor, raising it to the power, and I'm doing so. 5 squared is 25. Okay, here's the case where when we take a power to a power, we keep the base, in this case b, and we multiply the exponents. So 3 times 2 is 6. So the letter D is basically an extension of this concept, the power of a product rule, to 3 factors. And again, you could show this intermediate step where you take each factor, -3, raise it to that power, 4th power. The x to the 4th gets raised to the 4th, and the y gets raised to the 4th. And if you want to slide a 1 on the exponent of the y, that's fine. But then we evaluate -3 to the 4th. If you have to use your calculator, that's fine. That gives positive 81. And then here's the case where, again, we have to multiply the exponents. So we're taking a power raised to a power, so we need to multiply these exponents. So x to the 4 times 4 is 16. And similarly, y to the 1 times 4 is 4. Okay, moving on. Here we have the combination of all the rules, product, quotient to a power. So, again, the intermediate steps don't need to be shown. You could just jump right in there and start the exponentiation process. But basically, we're going to take each factor involved in parentheses and raise it to this power, the 3rd power. So the -2, and again, this is the intermediate step that if you wanted to skip, you could skip it. But the idea is -2 gets raised to the 3rd, the u to the fifth gets raised to the third, the v gets raised to the third, and the w gets raised to the third. So every factor raised to that power and kept as a quotient. So negative 2 to the third is negative 8. U to the fifth raised to the third, again we multiply the exponents here, so u to the 15th. This is v to the first, understood. If you want to slide the 1 in there, you can. Raised to the third is v to the third. And similarly, this is w to the first, raised to the third, would give us w to the third. Okay, and then we get into using the quotient rule here. What you could do is you could separate the factors. And again, all these intermediate steps, if you're comfortable, you could skip. But you could separate the common bases, x to the fifth over x cubed, separated from y to the seventh over x to the fourth. And then it's probably efficient here because the power in the numerator is greater than the power in the denominator on each of these. It's probably most efficient just to simply think about the quotient rule, where when we divide common bases, we keep the base and we subtract the exponents. So 5 minus 3 is 2, so we have x squared, and similarly y to the 7 minus 4 is 3. But then we get into some situations here. Well, in letter G, you have a fraction again. Now you've got some coefficients thrown in, and the coefficient in the denominator is actually greater than the coefficient in the numerator. So you might consider separating the coefficients from the common variables, the common variable factors. So we have 3 over 15 times p to the fourth over 4, p to the fourth times q to the seventh over q to the third. And you're going to reduce each one of these. 3 over 15 reduces to 1/5. Okay, p to the fourth over p to the fourth. Probably best to really just think about that as cancellation. That is, there's 4 factors of p here that cancel with all 4 factors of p down here. And so you just get 1 over 1 or 1. There's really not a need to even write that. Or you could think of the fact that when you divide common bases, you subtract the exponents. But then you would get p to the 0, but recall by definition, p to the 0 is 1. And then q to the 7th over q cubed. Again, you could think about division as common bases, you'll get q to the 4th. But thinking about it in terms of cancellation, you have 3 factors of q in the denominator that you're taking away from the 7 factors of q that are in the numerator. So you'd be left with q to the 4th in the numerator. And that's over 1 then. And then we can multiply across, and we get q to the 4th over 5. Now, that's cancellation technique's very convenient, because when you have a situation like this, let me first recopy. So we can separate the coefficients. I'm going to separate the common factors of a squared over a, and then b over b to the 5th. Okay, when we reduce 3 over negative 18 over 3, we get negative 6 over 1, or you could just simply say negative 6. Okay, now here, again, you can think about division of common bases, but I'm going to think about it in terms of cancellation, and I'm taking 1 factor of a away from 2 factors of a, so I'd be left with 1 factor of a in the numerator, or a to the first, and then thinking about b to the first and b to the 5th. This is where cancellation comes in handy. That is, when the denominator has a power that's greater than the power in the numerator, thinking about it in terms of cancellation would be as follows. You're going to cancel 1 factor of b from the numerator, with the 5 factors of b that are in the denominator, so you're basically taking 1 factor away from b to the 5th, and you're left with b to the 4th. Okay, so here we have a to the 1st over 1, or just simply a over 1, and then here 1 over b to the 4th. And then when we multiply across, we get negative 6a over b to the 4th. And again, you don't need to show this middle work. You could actually just jump right in here and start the cancellations within the context of the given situation. Okay, so that's exponent rules and a few more. We call negative exponents mean reciprocals. So 9x to the negative 8th. The only thing the negative exponent of negative 8 is operating on is the x variable. So if you wanted to, you could think of it as 9 times x to the negative 8th. And then use the negative exponent rule on x to the negative 8th. Becomes 1 over x to the 8th. And then we could express this as 9 over x to the 8th. Or just simply skip these middle steps and realize that when you have a negative exponent in the numerator, it just simply shifts to the denominator and the exponent becomes positive. And that's basically what I'm going to do here. I'm not going to show it literally. I'm going to do the exponential shift. This contains both concepts. The one we just explained, where if there's a negative exponent in the numerator, it's going to shift to the denominator and the exponent becomes positive. And then if there's a negative exponent in the denominator, it's going to shift to the numerator and the exponent will become positive. So just understanding those concepts, the x to the negative 5th goes to the denominator and becomes x to the positive 5th, and the y to the negative 7th that is in the denominator shifts to the numerator as y to the positive 7th. Okay, we've got scientific notation now. And remember, if we're converting from standard form to scientific notation, we want 1 non-zero digit before the decimal point. So, actually, let me rewrite this so I can draw my little arrows efficiently. Okay, so 0 point, there's 1, 2, 3, 4, 5 zeros. 1, 2, 3, 4, 5 zeros, then 6, 1, 8. Okay, in scientific notation, we want to place the decimal point so there's just 1 non-zero digit before it. I like to put a little arrow in there. And so I want to move the decimal point to where it would be between the 6 and the 1. And then we basically just count. So we could actually start off the answer by saying that this would be 6.18 and then times 10 raised to some power. And that power is determined by counting how many places we move to the decimal point to get to the position where our arrow is. And so we count the places. I'll use little loops here. 1, 2, 3, 4, 5, 6 to get to this position. But recall that if the number is less than 1, the exponent on that base of 10 will be negative. So therefore negative 6. As opposed to this example where, okay, I'm going to recopy it just for the sake of drawing the arrows again. 406, 000, 000. And I know I want to put the decimal point between the 4 and the 0. Again, just 1 non-zero digit before it. So this is going to look like 4.06 and then times 10 raised to some power. And that exponent is determined again by counting how many places we move the decimal point in the original number to get to where our arrow is. And the decimal point originally follows the final 0, so it's right here. And counting 1, 2, 3, 4, 5, 6, 7, 8. So it took 8 positions, and if the original number is greater than 1, that exponent will be positive. So times 10 to the positive 8th. So remember, negative exponents, the number's less than 1. Positive exponents, the number's greater than 1. Which leads us to the reversing the concept, writing in standard form. So if I have 5.37 times 10 to the 7th, right away I know that this number is greater than 1 because the exponent is positive. Which also tells me then, when I write the number, if I want it in standard form, I'm going to move the decimal 7 places, but if the number is greater than 1, obviously we'd have to move to the right 7 places. So 1, 2, 3, 4, 5, 6, and 7. Okay, that's where you definitely need the loops, so you can put our little placeholders of zeros. And so then we get 5, 3, 7, 0, 0, 0, 0, 0. And then if you like, every 3 digits from the right is a period, where you could separate the numbers by commas. So 53,700,000. And then when you look at this example, you know immediately, because of the negative exponent, that the number is going to be less than 1. So therefore, we're going to be moving our decimal point to the left. So I'm going to give a little bit of room here, since I know I'm going to go to the left, because the negative exponent. And write down the 9.12, and then to the left 5 places. 1, 2, 3, 4, and 5. There's the decimal point in our answer. Fill in the placeholders, zeros. And when I have a decimal number with no whole numbered portion, I always like to write a 0 in front of the decimal. That's just good practice. You don't have to, but I'm going to write 0 point, and then there's 1, 2, 3, 4 zeros, and then the 912. Okay, so then we get to polynomials. And here we're adding or subtracting. First one's just like terms, no parentheses. Just identify your like terms. There's a 7p squared, a negative 9p squared. We combine those. I mean, you could actually, I'll show this once. You could actually group the p squareds together and the constants together and then combine. But I like to do the little bookkeeping method without that middle step. 7p squared minus 9p squared is minus 2p squared. And then a negative 4 combined with a negative 3 gives us a negative 7. So in the future I'll be doing it that way rather than the grouping. But if you feel you need to group, by all means group. Okay, when you have addition of 2 polynomials, because that's basically what we have here, there's addition, and these are 2 polynomials, I'm going to rewrite it just so I could show more effectively the concept. And the concept really is rather simple, because what we're going to do is we're going to think of what's out in front of the parentheses as ones. Because we know if nothing is written, it's a 1. And then you could think of the distributive property. And here we're distributing to each of the 3 terms in the set of parentheses. But it's almost silly to think of it that way, because If you're just distributing ones, nothing's changing. So effectively, you could just drop the parentheses, because 1 times 9a squared is 9a squared, 1 times negative 7a, negative 7a, 1 times 3 is 3. Similarly, 1 times 4a squared plus 4a squared, 1 times negative 5a, negative 5a, and 1 times negative 8, negative 8. So you could equivalently just drop the parentheses and start identifying like terms. So we've got the a squared. Remember, you want to go for highest power first. So there's 9a squared and 4a squared combining to 13a squared. There's a negative 5a, 7a, I'll underline them twice, the a's that is, and a negative 5a, which combine to give negative 12a. And then there's the constant terms. I don't know, maybe circle them. You can underline them 3 times, whatever you want. And a 3 and a negative 8 combined to give negative 5. Okay, I am going to show, once again, recopying this, I am going to show the distribution. And here, it does make a big difference. Because when we think of these as a 1 out in front of this binomial, and a negative 1 out in this front of this trinomial, when we distribute, well, 1 times anything is itself, so it doesn't really change the first 2 terms at all, because 1 times 3x squared is 3x squared, and 1 times negative 7 is just negative 7. But it does make a difference on the terms that are being subtracted, because it's a negative 1 that we're distributing to each of these terms, and a negative 1 times a positive 4x squared is a negative 4x squared. A negative 1 distributed times the negative 5x is a positive 5x, and the negative 1 times 2 is negative 2. And now we can combine like terms. So we got the x squared, we'll add together first, or combine 3 and negative 4 of them to give negative 1x squared, or just simply negative x squared. The 1 is understood. Next thing we expect to see, because we should try to adhere to the convention of descending order of powers, after a squared term we expect to see a linear term, and the only linear term, or x term, so that was the x squareds. The only x term is that positive 5x. Sorry, I didn't mean to underline that again. It was just underlined once because it was the x squared. So the only x term is the plus 5x, so we just bring it down. But then we can combine these constant terms, the negative 7 and the negative 2, to give negative 9. Alright, and then here is just an extension to 3 polynomials that are being added or subtracted. Just for the sake of being thorough and consistent, I'm going to recopy and slide my little ones in front of the set of each set of parentheses. So there's a 1 out in front of here, plus 1 there, but then a minus 1 there. Now again, when we distribute the 1s, really doesn't change anything in the first 2 polynomials, because 1 times x squared is just x squared, 1 times negative 3x, 1 times 3x squared, positive, 1 times negative 5x, and 1 times positive 2, positive 2. But here's where we be careful, because a negative 1 times 7x squared is a negative 7x squared, and then the negative 1 distributed times the positive 5 gives us a negative 5. Okay, and so then, like terms, let's gather all the x squareds. This is really a 1x squared that's understood. Plus 3x squared is 4x squared. Minus 7x squared would be minus 3x squared. Okay, we'll go with the x's next. Negative 3x, negative 5x, no other x's, and negative 3 and negative 5x combine to give negative 8x. And then finally the constant terms, looks like there's a positive 2 and a negative 5, that combine to give negative 3. Okay, next we get into multiplication. So that was addition, subtraction of polynomials, now multiplication. Initially it's just the distributive property, and now is where we're using our laws of exponents in combination with the distributive property. So this 3x is being distributed to the 5x and to the negative 7. Now, if I write an intermediate step here, like 3x times 5x minus 3x times 7, it makes it look much more cumbersome. So my suggestion is, although you could show it that way if you want, in the future I'm not going to be showing it that way, because my suggestion is you need to be proficient at the concepts. And multiplying common bases, first we multiply the coefficients. When we distribute 3x times 5x, 3 times 5 is 15, x times x, x squared. And then when the 3x is distributed to the negative 7, we get negative 21x. So that middle term you should be able to skip. And actually I think I'm going to skip it here. I'm just going to show the distribution of this negative 3a to the 5th. When I multiply it by 2a squared, negative 3 times negative 2 is negative 6. And we are multiplying common bases, so we keep the base of a, and we add the exponents. 5 plus 2 is 7. Then that negative 3a to the 5th is distributed to this negative 3a. And a negative 3 times a negative 3 is a positive 9. And that's a to the 5th multiplied by, if you like to slide the 1 in there, a to the 1st, which gives a to the 5 plus 1 is 6. Add the exponents again. And then that negative 3a squared is distributed to the 4. And that gives us negative 3 times 4 is negative 12. And we tag along the a to the 5th. Okay, so then the final page is a bunch more multiplication and finishing up with a couple divisions. So, looks like some examples of FOIL. So I'll rewrite this in the middle so I could show the FOIL process. Remember, binomial times a binomial is FOIL. Take the product of the first. X times x gives x squared. Product of the outers. X times negative 7, negative 7x. Product of the inners. Positive 4 times x plus 4x. And product of the last. Positive 4 times negative 7, negative 28. And then typically, remember, when we FOIL, the outers and the inners can often be combined. And here they can be. So make sure you combine those. We'll recopy the x squared. Combining a negative 7x and a positive 4x gives negative 3x. And then we just need to bring down that negative 28. Okay, here's one where the coefficients are a little bit more interesting, but it's the same process because, again, we have a binomial times a binomial. So the FOIL method. So product of the first, 3x times 2x. 3 times 2 is 6, x times x, x squared. Product of the outers, 3x times negative 5, that's negative 15, tag along the x. The inner product, negative 2 times 2x would give negative 4x. And finally the last. And a negative 2 times a negative 5 is a positive 10. And once again we see that the outers and inners can combine. So we have 6x squared, looks like minus 19x plus 10. Okay, then we get to a couple special products. And if you don't recognize this as the difference between two perfect squares, that's fine, because as long as you know how to FOIL, you can handle this by just multiplying the binomial times the binomial using the FOIL method. That is, we take the product of the first, and we get 16x squared, product of the outers, plus 36x, product of the inners, minus 36x, and the product of the last gives minus 81. But notice that the middle terms, the outers and the inners, that is, now cancel because they're opposites. So we get 16x squared minus 81. So you might recall that this is the difference between two perfect squares. And if you wanted to, by the shortcut method, recognizing it as the difference between two perfect squares, the outers and inners, you know, are always going to cancel. So you get just the product of the first, or 16x squared, and then plus the product of the last, which is minus 9 times 9, or minus 81. Or there's a method, and that would be to use the formula, which says to square the first term and then minus the square of the second term. And you can see we get 16x squared minus 81 that way as well. So a variety of ways to approach that problem, but I think the easiest one, well, probably the second one there, knowing if you recognize the inners and outers cancel. But I would say if you're not comfortable with that, just grind through the FOIL process. It brings you to the same result. And similarly here, we have a shortcut method to square a binomial, but I suggested you think of it as that binomial times itself, and then go through the FOIL process. So let me rewrite it here. 3x minus 2 times 3x minus 2, and we're just going to FOIL as normal. So we get 9x squared. I'm not going to put the letters in, I'll just do the distribution. 9x squared when we take 3x times 3x. 3x times negative 2, negative 6x. Negative 2 times 3x for the inners, negative 6x. And negative 2 times negative 2, positive 4 for the last. So we get 9x squared minus 12x plus 4 after combining the two middle terms, which turned out to be the same. Or the shortcut formula, where when you square a binomial, you square the first, take 2 times the product, so 2 times 3x times negative 2, and then you add the square of the second, so plus a negative 2 squared. And that gives us 9x squared, those give us 2 times 3 is 6, times negative 2, negative 12x tags along, and then plus squaring negative 2, we get positive 4. Okay, so again, it's your choice I think many students are a little bit intimidated by the shortcut formula. So my suggestion, if you're good at foiling, which pretty much you have to be, just rewrite it as, once you see it as a binomial squared, rewrite it as that binomial times itself and go through the FOIL method. Okay, here's a special one, a binomial times a trinomial. And it's really the double distributive property, an extension of the FOIL method, because this x now gets multiplied by all three terms. So x times x squared gives x cubed. X times a negative 2x, negative 2x squared. X times 3 plus 3x. That ends the distribution for that x. Now distribute the negative 3 evenly. Negative 3 times x squared, negative 3x squared. Negative 3 times negative 2, positive 6x. And negative 3 times 3, negative 9. And then we could add the like terms. Well, that's the only x cubed, so I'm just going to recopy it. The x squared, there's negative 2 of them, and negative 3 of them, which combine to give negative 5x squared. There's the x terms, 3x and 6x, combined to give plus 9x. And then there's just the constant term, negative 9, that needs to be recopied. Now, an alternative way to do this one, you basically do the same thing, but there's one little advantage to this method that I'm about to show. After we take these products of the first distribution of the x to get x cubed minus 2x squared plus 3x, we could take advantage of adding vertically and lining up like terms. So the first product we get when we distribute this negative 3 is negative 3x squared. So I'm going to strategically place it below the x squared that is generated from the x times the negative 2x. And I just noticed this was x times 3x. That should be a 3x at the end there. Or excuse me, x times 3 should give us 3x for that final product of the distribution of this x. Okay, and then, so that was the negative 3 times the x squared. Then negative 3 times negative 2x is a positive 6x. And notice how that lines up neatly with like terms under the x that was created from the distribution of that x. Alright, so that's that one, and then the final one, negative 3 times 3 is just simply negative 9, and that's off to the side on its own. And then you could add vertically. And you get x squared minus 5x squared plus 9x minus 9, and of course it's the same result. Okay, and then the last two questions are just basic divisions by a monomial. And remember, what we're doing is we're reversing the concept of combining fractions. And the easiest way to show this, you should take a step and rewrite it. This denominator gets divided into each term of the numerator. So 7x to the 5th gets divided by x, and then plus the 4x cubed gets divided by the x. And then you simplify. This is x to the 1st. Probably easiest just to think of division of common bases and subtracting the exponents. So we get 7x to the 4th. And similarly here, plus 4x squared. So then the final question, pretty much the same concept, but something slightly different, as we'll see. But everything, once again, gets divided by this denominator. And you should take a step to show this. So negative 10x to the 6th gets divided by the 5x cubed. The plus 25x cubed gets divided by the 5x cubed. And the minus 15 gets divided by the 5x cubed. And then here's, in this example, you want to think about, well, for the first term, negative 10 over 5 is negative 2, and x to the 6th over x to the 3rd. Think of division of common bases. Subtract the exponents to give x to the 3rd. But here in this next term, when you simplify 25 over 5, we get 5. But the x cubes you can think of as canceling. And so they go away. And then the only thing that we can do here is divide 5 into 15, 5 into 5 once, and 5 into 15 3 times. And so we'd have minus 3 over x cubed. Okay, so that's the end of it. That's what the exam's going to be like. And please take the problem set, do your best on that. Take it as many times as you like. My math lab only counts your best score. And then we will have our unit test on a date that is mentioned in class. So I wish you the best of luck on the exam.